Alright, in this video we're going to be kicking off Chapter 11, which is over three-dimensional space and vectors, by discussing Section 11.1, rectangular coordinates in 3-space, spheres, and cylindrical surfaces. So to get started, we just want to remind ourselves of the rectangular coordinate system. Throughout this semester, we're going to be talking about 3 dimensions. So we're very familiar in working in the XY Cartesian coordinate plane, but now we're going to be talking about the 3-dimensional Cartesian or rectangular coordinate system. So in particular, we're going to be talking about 3 dimensions, namely X, Y, and Z. You'll notice the orientation here where X is coming out of the page at you and Y and Z are situated in the plane of the paper. And then we have what's known as the coordinate planes. First, let's take a look at this XY plane. You'll notice that it slices through parallel with the X and Y plane, but perpendicular to Z. So it's always assumed that the Z coordinates of any points in the XY plane is 0. Similarly, the coordinates in the XZ plane all have the similarity that Y equals 0, and in the YZ plane we have that the X coordinate is always 0. We should be familiar with the distance formula from previous coursework. So if you have 2 points P1 and P2, whose coordinates are x1, y1, and x2, y2, then we can compute the distance between those 2 points in 2 space by taking the square root of the sum of the differences in each coordinate. So you'll notice that this is written as x2 minus x1 squared plus y2 minus y1 squared, and of course the square root over top, but it's worth noting that in fact the order of those differences doesn't matter. So you could just as easily compute this as x1 minus x2 quantity squared plus y1 minus y2 quantity squared with the overarching square root. And the reason being is these squareds here save you, because if you change your order of subtraction, that will give you a negative sign, but once we square it, the plus or minus doesn't make any difference. So the order in which you take these differences doesn't matter. Now, if we want to extend this into 3 space, we still are looking at 2 points, but now we're adding this Z coordinate to each of these points. And the only difference is we add that sum of the square of the differences of the Z coordinates. Otherwise, that distance formula is very similar. So we'd like to utilize the distance formula to solve the following problem. Whenever I enter a number here for an example, that means that I'm pulling it out of the textbook, and this is problem 11 from the homework problems in section 11.1. So part A, show that points P, Q, and R in 3 space are vertices of a right triangle. So the first question you want to ask yourself is, what is a property of right triangles that I can utilize to identify whether or not these 3 points do in fact form a right triangle? So the first thing you might think of is, okay, well, we know that 2 of these line segments must meet at a right angle. So do we have the tools in order to identify whether these line segments form a right angle? The short answer is not yet. We will get there later on in this chapter, but as of right now, we don't know how to calculate the angles between 2 line segments or vectors in 3 space. So instead, remember, they had asked us to use the distance formula. So what is a piece of information that we know regarding distances or lengths of a right triangle? And we can use the Pythagorean theorem. So I'll just note that here, use Pythagorean theorem. And so the Pythagorean theorem says that a squared plus b squared equals c squared, where c is, representing the length of the hypotenuse, or in other words, the longest side of that right triangle. So if we can calculate the lengths of these line segments between P, Q, and R, and if we can also show that those lengths satisfy the Pythagorean theorem, then we can conclude that they're vertices of a right triangle. So let's utilize the distance formula here to calculate the distance between each of these 3 points, each of the pairs. So starting with the distance from P to Q or Q to P, we had discussed that the order doesn't matter. And so I'll just take the coordinates of P minus the coordinates of Q, and I'm going to square them and add them all up. So the last one is 6 minus 9 squared. And we have this overarching square root. So this is the square root of 4 plus 36 plus 9. That becomes the square root of 49, which is 7. So now on to the next distance. I'm just going to choose to find the distance between P and R. All right, so from P to R we have 2 minus 8 squared plus 1 minus 5 squared plus 6 plus 6 squared. We had that double negative there, turned us to a plus. And so we have the square root of 36 plus 16, and 12 squared is 144. So 16 plus 144 gives us 160, plus 36 is going to be the square root of 196, and that is a perfect square that's equal to 14. So the last length we need to compute is the distance from Q to R. And so that is going to be the square root of 4 minus 8 squared plus 7 minus 5 squared plus 9 plus 6 squared. So this is the square root of 16 plus 4 plus 15 squared, which is 225. So 225 plus 20 is the square root of 245. That is not a perfect square, so I'm just going to leave it as that square root. And so finally, the question here is, does a squared plus b squared equal c squared? So remember, A and B are just legs of the right triangle, but C is the length of the hypotenuse. So now the question is, how do we identify what the hypotenuse is? The hypotenuse is always the longest side of a right triangle. So for one of our lengths, we had the square root of 49. Another length, we had the square root of 196. And for the third, we had the square root of 245. This is the largest length. And so it's going to represent C, the length of the hypotenuse. And so let's answer our question. I will just arbitrarily choose the first one to be A and the second one to be B, but you could flip-flop these if you want. They're just the two legs. It doesn't matter which one's which. And then, of course, the longest one has to be C. So A squared plus B squared would be 49 plus 196. And those add together to be 5 carry the 1, 14 carry the 1, 245, which is in fact C squared. All right, so we are in business. We know that triangle PQR is right, and that's because we just showed that it satisfied the Pythagorean theorem. All right, we have a couple more pieces to this problem. Part B says which vertex is at the 90-degree angle. So what we just discovered is that segment QR is the hypotenuse. And we know that the hypotenuse is always opposite the right angle. So angle P is the right angle. So our answer is P is the vertex of the right angle. And finally, part C, we want to find the area of the triangle. We already did all the hard work computing the distances, so we can just utilize our information there. So the area of a triangle is given by 1/2 base times height. But we're just going to use the base and the height as the two legs. So one of those lengths was 7, the other was 14. And so we get an area of 49 square units. All right, so that's a wrap on problem 11. All right, next we're going to move into circles and spheres. So I have a remark here to remind you of the equation of a circle. If we have a center x naught, y naught, then the equation of the circle is x minus x naught squared plus y minus y naught squared equals r squared. If we want to extend a circle into 3 dimensions, it becomes a sphere. So now we're adding a z coordinate for the center, which we have z naught, and the equation of the sphere has the 2 pieces from the equation of a circle with this added dimension here in z. So we have this plus z minus z naught squared, and we still have equals r squared here on the other side. So let's make use of this formula to solve the next problem. Use the distance formula and the equation of a sphere to solve the following problem. So problem 14 from the text. Find the equations of 2 spheres that are centered at the origin and are tangent to the sphere of radius 1, centered at the point 3, negative 2, 4. All right, so this is not required, but in order to come up with a game plan of how we're going to solve this, I find it helpful if we draw a picture. So what I'm going to do is I'm going to just sketch this picture up above. And I'm going to draw my 3-dimensional coordinate system, sticking with x coming out of the paper, y pointing to the right, and z pointing above. And what I want to do first is I want to plot this center, and then I will plot the sphere of radius 1 about that. So I want to go out 1, 2, 3 in the x. I want to go in the negative y direction. So I'm going to draw a negative y-axis coming out here, and I want to go 1, 2 in the negative y. And then from here I'm going to draw a little ghost z-axis, and I want to go up 1, 2, 3, 4 units. So here's my center, and then I want my sphere to have radius 1. So I'm going to do my best to accurately draw a sphere of radius 1. All right, so here's my little sphere. This is the sphere that we're given. We want to find the equations of 2 spheres centered at the origin that are tangent to this sphere. So the question is, how can you have 2 spheres centered at the same location, namely the origin, being tangent to the sphere that I have drawn? So there are 2 ways to do this, and I'm going to sketch these spheres in 2 different colors. One is if you touch the sphere at a single point here that's closest to the origin. So this sphere would look something like this. Close counts here for drawing. All right, so this sphere in orange is centered at the origin, and it's just big enough to just touch that sphere in one single spot. Okay, that's what it means to be tangent to the sphere. And for the next sphere, which I'm going to draw in green, if we want to still be centered at the same spot, namely the origin, but we want to be tangent in another place, we could just envelop that sphere and just touch it on the back side back here in one single place. So this sphere would look something like this. All right, so it's kind of hard to convey here in 2 dimensions, but this green sphere actually contains both the orange sphere, but also that black sphere, and it's only touching that little tiny black sphere in one place. It looks like it's cutting through here, but it's actually not. It's just a fault of drawing this in 2 dimensions. So it's completely enveloping that black sphere. So back to what we're looking for. We're looking for equations of both the orange sphere and the green sphere, but they're both centered at the origin. So if I come back up to this equation here, both of these spheres are going to have a center of 0, 0, 0. So this x naught, y naught, and z naught are going to zero out. The only thing that's going to be unique to these 2 different spheres is the r squared. So let's make note of this. Since the center is at 0, 0, 0, both equations are of the form x squared plus y squared plus z squared equals r squared. And we're just going to have two different radii for the green and the orange sphere. And so what's that radius going to be? Well, certainly we can draw it, right? Here's this orange radius, and similarly, we have a green radius, which goes out to here. So how can we determine that radius? Well, what we could do is we could find the distance from the origin to the center of the small sphere. And then what we're going to do is we're going to add 1 to that distance to get the green radius, which is just going out to the other side of the black sphere, and subtract 1 to get that smaller radius, which is just coming in 1 unit to get the orange radius. So what I'm going to do is I'm going to find the distance from the origin to the center of the black sphere, which is 3, -2, 4. So that distance, which I'll denote by d, is going to be the square root of 0 minus 3 squared plus 0 plus 2 squared plus 0 minus 4 squared. And so that's the square root of 9 plus 4 plus 16. So that's the square root of 29. It's an ugly number, but it's a number nonetheless. And so for your smaller radius, you want to subtract 1 from that distance, and for your larger radius, you want to add 1. And so my final answer here for the two equations are x squared plus y squared plus z squared equals the quantity square root of 29 plus or minus 1. And of course, we always want to square our radius. That plus or minus is going to determine whether you're talking about the orange radius or the green radius. So plus 1 is the green radius. Orange is going to be minus 1. And so I'll box that in for my final answer here. Okay. So we're coming up to our first theorem here. And what it's going to do is it's going to tell us the types of graphs that we can have for equations of a particular form. So the equations that we're looking at are of the form x squared plus y squared plus z squared plus these linear terms gx plus hy plus iz plus some constant equaling 0. And we have three possibilities for equations of this form. It's either a sphere, meaning there are infinitely many points that satisfy this equation, but they all lie on a sphere. It could be a point, meaning a single point in 3 space satisfies this equation, or there is no graph. No points in 3-dimensional Cartesian space would satisfy that equation. So what we're going to do in order to determine this is we're going to take these equations and we're going to write them in standard form, in a sense of writing them back up into this this format here. So let me clear this out here so that we can see it. All right. We would like to take these equations and write them as perfect squares here so that we can see, is this a sphere with a certain radius and where is its center? Or is it something degenerate like a point, or does it not have a graph at all? So we'll take a look at what those options might look at. So in order to put it into the standard form, we need to do what's called completing the square. So if you're a little bit rusty on that, that's okay. We'll go through it here together. What I'm going to do first is I'm going to collect all of the x terms. So x squared plus 2x, and then leave a space here to complete the square. And then similarly, combine the y and the z terms. So I have y squared minus 2y plus blank, z squared plus 2z plus blank. And then I'm going to kick this constant term 3 over to the other side. So I'm going to write minus 3 and then also leave a blank here. So here's how we're going to complete the square. We're going to take a look at the coefficient of the linear term. So in the case of the x's, that coefficient is a plus 2. I want to take half of that term and square it. So half of positive 2 is positive 1. When I square it, I get a positive 1. And I'm going to do this in all of these cases. Half of negative 2 is negative 1. Negative 1 squared is a positive 1. Half of positive 2 is a positive 1. Squared is a positive 1. Now, whatever I do to the left-hand side, I have to then do to the right-hand side. So what I ended up adding was 1 plus 1 plus 1. So in total, I added 3 to the left-hand side. So I also need to add 3 to the right-hand side. Now, the reason why we go through this process is because each of these sets of parentheses are now a perfect square. So you can always factor them to whatever your variable is, x, y, or z, and then whatever half of that middle term was. So it's going to be plus 1 and then quantity squared. Similarly, I have y minus 1 squared and z plus 1 squared. And right now, this is shaping up to be an equation of a sphere, but look at what happens over on the right-hand side. Negative 3 plus 3 equals 0. So you can think of this as a sphere centered at negative 1, 1, negative 1, but it has a radius of 0. In other words, that means that it's a single point. It has collapsed to a single point. So this is satisfied by the point at that center, which is negative 1, 1, negative 1. And you can always double check that this is correct by plugging that point back into the equation that you've gotten. Either the equation as it's written in the problem statement or your simplified equation after you've completed the square. All right, so our final answer here is a point. Let's do the exact same process for 28. Let's complete the square. So collecting x terms, I have x squared minus 2x plus blank. Then I have y squared minus 6y plus blank. And z squared minus 8z plus blank. And then I'm going to kick this 1 over to the other side. So that's a minus 1 plus blank. So let's complete the square. Half of negative 2 is negative 1. Negative 1 squared is a positive 1. Half of negative 6 is negative 3. Squared is positive 9. Half of negative 8 is negative 4. Squared is 16. So in total, I added 1 plus 9 is 10. Plus 16 is 26. So I added 26 over here. And now let's write this into standard form. X minus 1 squared plus y minus 3 squared plus z minus 4 squared equals 25. This is, in fact, an equation of a sphere here. And we have a nice perfect square on this side, so we have a radius of 5. So this is a sphere with center at 1, 3, 4, and radius equal to 5. So we saw an example of a point and a sphere. I just want to make note here that the way you could have an equation having no graph is if when you put it into standard form, the r squared term is negative. So of course you can't have the sum of 3 squares adding up to be a negative number, and so in that case you would conclude that in fact the equation would represent something that does not have a graph. All right, to conclude this section, we want to talk about cylindrical surfaces. That's the last topic. And so we have a definition here: the process of generating a surface by translating a plane curve parallel to some line is called extrusion. Surfaces that are generated by extrusion are called cylindrical surfaces. All right, so I want to kind of flush out what this whole extrusion process means, but I think it's best exemplified just by looking at an actual graph in space. So we're going to get to that in our next examples, but first, this last theorem, 11.1.2, says an equation that contains only two of the variables x, y, and z represents a cylindrical surface in an x, y, z coordinate system. So notice only two of the variables. That means one of those three variables is missing. The surface can be obtained by graphing the equation in the coordinate plane of the two variables that appear in the equation and then translating that graph parallel to the axis of the missing variable. So in other words, what they're saying is identify what two variables you're working with, graph that line or curve as if you were living just in two space. But because we're talking about 3 dimensions, you then want to translate the graph parallel to the axis of the missing variable. So let's take a look at what that looks like here in 37 so that we see what this means. So sketch the surface in 3 space, that's crucial. 37, z equals 1 minus y squared. So we're just going to note here that the variable x is missing. So what we're going to do for a moment is say, okay, let's just pretend like the x-axis isn't here. Now, of course, it is there, but for a moment, let's pretend like it's not. What is this an equation of in 2 space? This is a parabola that has been shifted up 1, and then that negative in front of the y reflects it across the y-axis. So just go up 1 on your z-axis, and then sketch a downward facing parabola. All right, this is what it would look like if we were just living in the YZ plane. However, we want to sketch this in 3 space. So this is where this last line of the theorem comes in. We want to translate the graph of this parabola parallel to the axis of the missing variable. In other words, we want to extrude it along that missing axis. So what I'm going to do is I'm going to take the endpoints of this parabola and I'm going to extrude it parallel to that missing x-axis. And then I'm also going to extrude the top here. And then I am just going to connect it with another parabola that is just parallel to the one that I just plotted. So if you want, you can draw in some more surface curves here to kind of give it that more 3-dimensional feel. But what this looks like is it looks like just a curved or bent sheet of paper. Now, what we do know is this parabola goes on for infinity. So if you wanted to make your parabola longer, right, then the whole thing would just look a little bit longer. Right, something like that. So it doesn't have to look exactly like mine. You could also extrude it along the x-axis coming out at you. So instead you could go in this direction. All right, and then you could draw some of these guidelines in here. So I just want to express here that what my graph looks like might not look exactly like your graph, but as long as I can see the surface and that you extrude it in the correct direction, that's what I'm looking for. So let's take a look at 39 here. We have 2x plus z equals 3. What I'm going to do is I'm going to solve for one variable. Let's write it as z equals negative 2x plus 3. Now we want to plot this equation in the xz plane. So again, we're just going to, for a moment, pretend like that y-axis isn't there, and we'll deal with that in a moment. But this is an equation of a line in the xz plane. So let's plot that line. We have a z-intercept of 3. So 1, 1, 2, 3. All right, and then what would our x-intercept be? So if I plugged in 0 for z, my x-intercept would be 3/2. So we're halfway between 1 and 2. And then just graph that line segment. Now again, this line goes on for infinity. I'm stopping it right here, but you could make it shorter or longer. And then we want to extrude along the missing variable. So the missing variable is y. So you could go in the direction of the y-axis. You could go in the negative y-axis. And then you want to take that line and parallel to the line you had just drawn, extend it. So this is just a slanted plane here that's slicing through exactly as shown. All right, for our last example, 41, this is relying back on your understanding of conic sections. So first, we see that the y variable is missing. I'm going to put this into standard form by taking this entire equation and dividing through by 36. So that's going to give me x squared over 9 plus z squared over 4 equals 1. And this is in fact an ellipse in the xz plane. So 9 is just 3 squared, 4 is 2 squared. So I want to go out plus or minus 3 in the x direction. And I want to go plus minus 2 in the z. And just draw that ellipse there. And then I want to extrude this along the missing variable y. So I'm going to go to the left, but again, you could go to the right just as well. And then kind of draw that ellipse there. And if you want, you can draw some little lines to kind of indicate the three-dimensional shape here. So this would be considered a cylindrical surface of an ellipse being extruded along the y-axis. So this concludes our notes for 11.1. Next up, we'll be talking about 11.2, so stay tuned.